Now we're going to look at examples of free damped motion and recall that our second order linear differential equation model for this type of motion is given by this equation. We have Fx of t is the displacement of the mass spring system. We have the second derivative of x with respect to t, plus this term 2 lambda dx dt, this comes from damping, plus omega squared x equals 0, with the relationship that 2 times lambda is your damping constant divided by m, and that omega, which is your circular frequency, its square is the spring constant divided by the mass. So we're going to look at all three cases mentioned in the previous video. We're going to look at overdamping first. This is the case where your lambda squared minus omega squared is greater than 0. So what's interesting is you can take an equation for which you've derived, or at least you think you have a model, and before you even solve it, you'll know which of the three cases you're going to have in terms of your damping, based on the coefficients that are in front of the dx dt term and x. So here's a particular case where the mass is released from, let's say, position 1 below equilibrium. So equilibrium, remember, is position x equals 0 after it's settled down, and then we have pulled it down. So that's what this diagram looks like. It's been stretched down to x equals 1, and we're doing it with a downward velocity of 1 foot per second. And if it's downward, that means it's the direction of the motion of the mass system. So that means we'll put a positive 1. So x of 0 is 1, and x prime of 0 is positive 1. It turns out, if you go ahead and use our Hooke's law and Newton's second law, you can derive this equation. We're going to do that with the other cases, but for now, this is the equation of motion that describes this particular system. So it's the second derivative of x with respect to t plus 5 dx dt plus 4x equals 0. And those are our initial conditions. What I want you to realize now is look immediately what the relationships are between lambda squared and omega squared. Remember, omega squared is the term right here in front of the x, so we know that's equal to 4, or omega is equal to 2. But over here, 2 lambda must be equal to 5. Well, if 2 lambda is equal to 5, then clearly we know that lambda must be 5 halves, which means that lambda squared must be 25 divided by 4, and clearly that is bigger than 4, which is 16 divided by 4. So we definitely have an overdamped case. This term right here is producing a lambda squared that is much bigger than omega squared. If you went ahead and solved it, take the auxiliary equation for that homogeneous case, and take the two roots, use your initial conditions to get the constants, you would get a solution of this form: 5/3 e to the minus t minus 2/3 e to the minus 4t. What's important here is to realize as time goes to infinity, both of those terms are going to 0. So clearly an overdamped system is it's not going to oscillate very much at all. It's slowly going to just come to a grinding halt. It's overly damped. Not much oscillation, if any at all. Right, that's the first case. Now let's look at a critically damped system. So here's a critically damped system. Again, I'll give the equation and then we'll derive it this time so we can see where it comes from. So in this particular case, we're looking at lambda squared and omega squared being the same. Suppose the mass now is 8 pounds, stretches the spring 2 feet with a damping force equal to 2 times the instantaneous velocity, and assume the mass is released from the equilibrium point with an upward velocity of 3 feet per second. So you're kind of pushing it up, so to speak. So first of all, the initial conditions, if it's released at equilibrium point, then we know that at time 0, we're at position 0, so x of 0 is 0. But here's that pushing. X prime of 0, the initial velocity here, is a minus 3 because it's upward. It's against the direction of motion of the spring system, which would be down. This turns out to be the equation of motion, second derivative of x with respect to t plus 8 dx dt plus 16x equals 0. So quickly we can read off omega squared must be 16. Well, then 2 lambda must be equal to 8, right? So then lambda is 4. So if you squared 4, you get 16, and hello, there you go. They're both the same. So this is an example of a critically damped system. Both those terms are the same. Let's derive the equation just from the principles that we have in terms of Hooke's law and Newton's second law. If it weighs 8 pounds, and it stretched, when you added the weight, it stretched the string 2 more feet, then we know that 8 must be equal to k times 2 from Hooke's law. So the spring constant must be 4 pounds per foot. We know that weighs the mass weighs 8 pounds. So if we normalize by 32 feet per second squared, we can get a quarter slug on the mass. Then we just use Newton's second law, mass times acceleration, 1/4 times the second derivative, has to be the other forces, has to balance out the restoring force of the spring and the damping force. And remember, the damping force is always going to be in the opposite of the direction of motion, so this needs to be -2. So when you clean up this, pull everything left side, multiply it by 4, you will in fact get the equation of motion that I had earlier. This was the equation we were deriving, and there we are. There it is again. Because the auxiliary equation will have a double root, the solution will have this form, C1 e to the minus 4t plus C2t times e to the minus 4t. Use your initial conditions to show that the first constant actually is 0, the second one is -3, and that is your equation of motion. What's interesting is as t goes to infinity, that's going to go to 0 as well. But before you go to 0, you are multiplying by t, which sort of indicates it won't quite go to 0 nearly as fast as the overdamped case. And we'll see a graph of these in just a second. So that's a critically damped system. Last case we're going to look at, underdamped. An underdamped system corresponds to this relationship between the lambda squared and omega squared. Or that you could say that the omega squared term is bigger than the lambda squared. Well, let's look at a heavier mass, 16 pounds, attach it to a 5-foot spring. So here you're given information about the length of the spring, but you need to know when you attach the mass, how much does it move? Well, it says at equilibrium, the spring measures 8.2 feet. So now you know how much it must have stretched after you added the mass. And we'll have a picture in just a second. Assume the mass is initially released 0.2 feet above the equilibrium point, so now we're kind of pushing it up. And then assume the damping is equal to instantaneous velocity. So the scenario we're going to have here is that when you attach the mass to the spring, it stretches out. The length becomes 8.2. If the original length of the spring was 5, then we know the displacement must have been 3.2 when you attach the mass. So that's important because now we can go to Hooke's law, force equals k times the s there, and derive that the spring constant must be 5 pounds per foot. Use our same analysis for the mass. Take your weight, divide it by the gravitational constant, 32 feet per second squared, and you'll get a half slug. So according to the Newton's second law, mass times acceleration must be the sum of the other forces acting on the system. The restoring force of the spring must be minus 5x, according to Hooke's law. And then we subtract off the damping, which is assumed to be the same as the instantaneous velocity, or just 1 times dx dt. Pull the terms to the left side, multiply by 2, and we will derive this equation. Second derivative of x with respect to t plus 2 times dx dt plus 10x equals 0. Notice this term on the right next to the x, this coefficient is so much bigger than the damping term there, the coefficient in front of the dx dt. So omega squared is 10, 2 lambda must be equal to 2, so lambda squared is just 1. Clearly 1 is much less than 10, so this is definitely an underdamped system. If you were to look at the auxiliary equation here for this particular system, as specified here, m squared plus 2m plus 10 equals 0, you'll get complex roots, -1 plus or minus 3i. Use what we know about solutions to second order homogeneous problems when you have complex roots. It'll be the form minus e to the minus t times some constant times cosine 3t plus c2 times sine 3t. Use your initial conditions. Remember, we pushed it up 2 positions above equilibrium, so that means x of 0 is minus 2. And we'll assume initially there is no initial velocity on it. So you'll get a constant c1 is minus 2 and c2 is 2/3. And that is what your displacement equation will look like for this underdamped system. E to the minus t times, in parentheses, minus 2 cosine 3t minus 2/3 sine of 3t. So you can see some sort of an oscillatory type of behavior here. Clearly, this will go to 0 as t goes to infinity. But before it goes to 0, notice it's going to oscillate, hence underdamping. So what I'd like to do is to show you a graph of all 3 of those equations of motion You zoom out just briefly here so you can see the graph. And if I show you the graph of all three in colors, you may not be able to see the colors, but I'll just point them out. In blue here is the graph when we were overdamped, and you can see very little, if any, oscillation as the x-axis is time. This is in seconds, 1, 2, 3, almost 4 seconds, and the system's almost stopped. This is the displacement, what position it was in. The red curve, which is this one here, is underdamped. And underdamped, you see the oscillatory behavior, but you can see the amplitude starting to drop. And again, after about 4 seconds, it's starting to rest. It's going back to equilibrium point. But you see the oscillatory motion, remember the parentheses terms that have the cosine and sine terms. And then the green, which is this very last middle one, is your critically damped. Has a little bit of oscillation going on, but settles down very, very quickly. If you released some of that damping, in other words, decrease some of the coefficients there, then you would get more of an oscillatory motion. But these three graphs illustrate all the free damped motion cases that you would have of a mass spring system.